So let's solve this question. If f1, f2 and f3 be the functions of x, y, z, suppose that for every given pair of points a and b in space, the line integral f bar dot dr bar evaluates to the same value along any path c that starts at a and ends at b, then which of the following statements is or are true, of course. Okay, so let's see. Given f1, f2, f3 are functions of x, y, z, are functions of x, y and z, of course. So it's given the integral, the line integral over c f1 dx, f2 dy, f3 dz, which can be written as integral over c f bar dot dr bar for f is equal to f1i, f2j plus f3k, of course, and dr is equal to dxi plus dyj plus dz k, of course. Okay, so if this is the case, is path independent, is path independent, correct? So this is path independent, of course. So if this is path independent, because they have clearly given you evaluation the same value along any path. Okay, so if this is path independent, then definitely this implies f bar is a conservative field, because basically in the conservative fields, if you move charges from one point to another point, then ultimately the work done in doing so doesn't depend upon the path. It depends only on the initial and the final positions. Okay, so f bar is a conservative field. So this implies curl f is equal to 0, first of all, point number 1. So let's see, for every closed path psi, we have for every closed path gamma, we have cyclic integral gamma f bar dot dr bar. So ultimately, so cyclic integral over c. So first question, option A, of course. Okay, so option A, you can see cyclic integral over gamma f1 dx plus f2 dy plus f3 dz. Okay, so this is what you got, f1 dx plus f2 dy plus f3 dz. So this can be written as cyclic integral over the gamma f bar dot dr bar, which can be written as integral over the surface S curl f bar dot n cap ds. Okay, which is equal to 0, of course. The reason is this term is actually 0, curl f bar is 0. This is basically the Stokes theorem. Okay, so this is the Stokes theorem. So ultimately, if a and b are coinciding, then ultimately the integral will be 0. There exists a differentiable scalar function phi f such that f1 equal to dou f by dou x, f2 equal to dou f by dou y, and f3 equal to dou f by dou z. Yeah, 2, because so this implies there exists a scalar function f, a scalar function. Okay, we'll write this as a separate statement maybe. So b, coming here, b, since curl f is equal to 0, this implies there exists a scalar function f, a scalar function f such that this f bar is actually given by gradient of the scalar point function. Okay, so this vector point field can be represented as a gradient of some scalar point function. So that's what we have. So this is also to x, y and z for 1, 2, 3 correspondingly. Then divergence is equal to 0, need not be. Okay, so actually the curl is 0, so but not divergence. Okay, so see, curl of f is equal to 0. That's it. Okay, this is what we know. We can't decide on divergence because we have fields which are irrotational, but they still have divergence. Like for example, if you have a charge, there could be location where there could be charge movement, but there could not be rotation of this charge. Things like that can be possible. So divergence is equal to 0, because this term ultimately means divergence equal to 0. No, that's not there. Curl of f is equal to 0. So if curl of f is 0, d curl f is equal to 0, this implies I j k dou by dou x dou by dou y dou by dou z f1 f2 f3 is equal to 0 bar, of course. Okay, so if this is 0, then ultimately dou f2 by dou x should be equal to dou f1 by dou y, dou f3 by dou y is equal to dou f2 by dou z, dou f3 by dou x dou f1 by dou z. This is what you have, of course. Okay, so if you check the options, dou f3 by dou y is equal to dou f2 by dou sorry, something is given. I think here there is a comma. It's a comma sign. Okay, it's a comma sign. So dou f3 by dou y, so dou f3 by dou y is equal to dou f2 by dou z. This first part is correct. Then f1 z and f3 z, yes, this is also 2, f2 y and f1 x, so this is also 2 actually. Okay, so option D is also correct. A, B, D are correct undoubtedly. Yeah. Okay, thank you.